Okay, so this is video 2, section 3.6, and we're going to start with example 2 from the PowerPoint. So area of the rectangle. We have a rectangle which has one corner in quadrant 1 on the graph of y equal 25 minus x squared, another at the origin, and third on the positive y-axis, and the fourth on positive x-axis. So with this problem, we actually have a nice graph. So you guys have that on PowerPoint. Let me show you the graph. So we have in y, x, and the graph goes by 10. This is 10. Here you have 20. This one looks like 25, but again, I'm not sure because they not really provide you anything. Here we have 5. Okay, so we have a rectangle like this. Okay, mine it's not in a scale. Okay, this is origin 0, 0. Okay, doesn't really. Okay, and this point right here, it's x, y, and this point belongs to the graph y equal 25 minus x squared. So 25 minus x squared is the parabola which opens down, and we only see the part of that graph. Okay, and we have an origin. So going back to this example, rectangle has one corner in quadrant 1. Okay, so one corner in quadrant 1 on the graph. So they're talking about this point right here, y equal 25 minus x squared. Another at the origin right here. A third one on positive y-axis right here. And the fourth one on positive x-axis right here. Okay, so we have a rectangle. And this is what we need to do. A, express the area A of the rectangle as a function of x. So again, we need to express the area of the rectangle as a function of x. Okay, so let's write the solution. Okay, so area of the rectangle, okay, it's length times width. Length times width. So this is the length, this is the width. So of course we cannot use L and W, we need to use only variable x to express the area because we need to build the function in terms of x. Okay, so how are we going to do it? Let's talk about L, which is the length. So the length of the rectangle right here, it's going to be expressed using the x coordinates. So again, I cannot really read that point. I don't know if this is 3, if this is 3.5, or this is 4. So again, the length, it's being expressed using x values. Okay, so for length, length we're going to use x. Okay, this is length. Okay, let's talk about width. width. Width, okay, so the width of this rectangle, like you see, it's been represented by y values. That's technically the height of the graph. So width it's been expressed using y values. So what's going to be the width of this rectangle? You cannot say it's 15, maybe it's 18, because we don't really know. So width, it's going to be expressed using y. And what we know about the width, okay, look what happened. This is the width of this rectangle right here. So look what happened. This point, the y coordinate right here will give us technically the width of the rectangle. So what we know about this y, that this y right here satisfy this equation. Y is the same as 25 minus x squared. So what we're going to do, replace y from a point, and I'm going to label that point so we all know that we're talking, let's say, point B. From point B with the given equation. This point belongs to the graph y is equal to 25 minus x squared. So y coordinates satisfy the equation 25 minus x squared. So you can think about point B, have coordinates x, and we're replacing that y with 25 minus x squared because it belongs to the graph of the function 25 minus x squared. So width of the rectangle, it's going to be represented as 25 minus x squared. This is the y values, but again, y values we can calculate based on this problem using the given equation, which is 25 minus x squared. So knowing those information, this is w, x it's L. Okay, so we're going to create, okay, area. So area equal length times width, but in our case, area, it's equal. Length is just x times width. Width, it's 25 minus x squared. Simplify, so we're going to distribute x. So area, it's equal 25x minus x to the third power. So what happened? We just built the function in terms of x. This is how you can calculate the area of the rectangle. Don't forget that you only have a picture, okay? So technically we can also build the rectangle, which will be, oops, sorry. No, that's not what I wanted. Okay, so don't forget that you can build also a rectangle which may look like this, okay? Or going back to this problem, we can build a rectangle which will be looking like this. So we don't really know exactly about which rectangle they're talking about, okay? Oh, okay, what I just did. Okay, going back. Give me a second. I still want to work on it on this page. Okay, so let's go home. I'm doing drawings. Okay, so we have an area. Okay, so we did express the area A of the rectangle using function of x. We have it. Okay, this is the area of the rectangle express is a function of x. Perfect. So now we can move on to B, part B of the problem. In B, they want you to figure out what is the domain of A. Okay, so what is the domain of area? So again, domain, don't forget that we're going back to the graph. That's your x values. Okay, so we have to check what will be the domain. Let's go back to our graph. So here, this is our domain based on the x values. Okay, and the graph gave you that point right here. So our x values are from here to here. So the domain will be from 0 to 5. Oops. From 0 to 5. That's the domain. Okay. Graph A equal A of x, and for D, for which value x has the area, which is the largest one. So for graphing, let me just write the note. C and D from PowerPoint. Read it. Read it. So I have to skip it. Because you need graphing calculator. TI-84 or TI-83 graphing calculator, which technically we should not use in this class. So they're asking you to find the maximum. Again, this is something what we need to do it with graphing calculator. So I'm moving on to the next example. So I will pause the video for a second. I will copy that example and I will go back. Okay, so just give me a second. Resume. So I'm continue. Okay, so next example, we're going to talk about the planes. So suppose two planes are flying at the same altitude, are headed toward each other. One plane is flying due south with a speed of 400 miles per hour, and it's 600 miles from the potential intersection point. Okay, so this is important. Then we have the other plane is flying west with a speed of 200 miles per hour, and it's 400 miles from the intersection. Okay, and this is what they ask you to do. Okay, so first let me maybe draw the picture of this situation. Come on, picture. Okay, so we have a plane 1 right here. Okay, and the first plane is flying south. Okay, what we know about the plane 1, so this is plane 1. Okay, so what we know about the plane 1, we know his speed. Okay, so his speed, I will put speed 1. So we know we're talking about this plane is 400 miles per hour. And we know that is 600 miles from potential intersection. Okay, so it's 600 miles from potential intersection. Okay, so we'll talk about that intersection point in a second. Okay, so then we have a plane 2 somewhere here. Okay, that's the plane 2. And plane 2, it's flying west. Okay, we know that plane 2 has a speed of 250 miles per hour, and it's 400 miles from potential intersection. So at the beginning, if we will stop time, plane 2 will be 400 miles from intersection. This is the intersection point. And plane 1, if we'll stop at time, okay, will be right here. Okay, come back. 600 miles. 600 miles from potential intersection. So it looks like the planes can crash. Okay. Okay. So what we need to do. Okay. So that's the problem. So I draw the situation for you, and let's start solving. A. Okay. A. Just put it here. Build a model that expresses distance d between the planes. Okay, between the planes is a function of time t. So this is important. So right now we're trying to express everything using variable t. Okay, so let's go back to that picture. So we have to build a model that expresses the distance d. Okay, so going back to our problem, the distance between two planes will be right here. This is our distance d. Okay, distance. Okay. So to be able to solve that problem, we need to review distance formula. So let's review that distance. It's equal rate times time. And again, rate, this is just a speed. You can rewrite that as speed times time. So t will represent time. T is time. We have no information about the time, how long the plane are flying, what will be the time when they will meet at that point right here in orange. So we have to introduce variable t for time. Okay, so what we know distance, which is 600. So this is distance at the beginning, before the planes will intersect at this point right here. And plane 2, the distance from the point of intersection at the beginning, it's 400 miles. Of course, the distance will decrease because the planes are moving, they're flying. So from original distance, plane 1, which is 600, and 400 is original distance for plane 2, we will need to subtract the distance with respect to time. Okay, so of course that distance will be decreasing. So before we'll do that, hopefully everybody see that we have a right triangle. So we need to express the distance, okay, which is hypotenuse of the right triangle. So All we know about the right triangle is that you can always use the not quadratic form, Pythagorean theory. Okay, so solution from Pythagorean theory. We know that a squared plus b squared is equal c squared. So in our case will be a squared plus b squared is equal distance to a second power. A, it's a distance of plane 1, B, it's a distance of plane 2. Okay, now, so let's talk about our case. So let me just rewrite that distance squared is equal A squared plus B squared. Okay, okay, let's just write this way. Oh, okay, going back. What just happened? Draw. Where's my drawing? Okay. Recent page. Let's go back to home. Hold on, let me pause that video. Okay, so I'm going back. So A, again, let's put it here. A, it's a distance of plane 1 from the point of intersection. And B here represents the distance of plane 2 from the point of intersection. Okay, so going back here to this problem, so original distance of plane 1 is 600 miles. So that t squared is equal 600 miles minus, however, again, the distance it's changing, okay? It's getting smaller and smaller. Okay, so the distance formula, it's rate times time. So the distance of plane 1, when we talking about the time, it's going to be the rate, which is the speed, times time. So the speed of plane 1, it's 400 miles per hour, okay? So distance 1 is 400 miles per hour times time. So from my original distance, which was 600 miles, I need to subtract 400 t. And I'm plugging in that into my formula. Okay, because we're expressing the distance between two planes using Pythagorean theory. Okay, so you cannot just say 600 square plus 250 square, which is the original distance of plane 2. We have to subtract, because the time it's keep moving, that distance will be getting smaller and smaller. Plus the b squared, this is how we're going to express. Okay, this is your plane 2. Originally, the distance was 400 miles. But of course, that distance will be decreasing with time. So the distance of plane 2 will be speed, rate times time, which is 250 t. Okay, minus 250 t to a second power. Okay, so the distance of plane 2, it's again 250t, and you subtract that from original. Okay, so this is the formula, and of course, to get d by itself, you just need to take the square root. So we're having 600 minus 400t to a second power plus 400 minus 250t to a second power. Okay, so this is what we have from part A. We build a model that expresses the distance d between the planes as a function of time. So this is the distance d between the planes as a function of time t. Of time t. Okay, now let's talk about B. Part B, they asking you to use the graph utility. They ask you to actually graph it. D, it's equals square root of 600 minus 400t square plus 400 minus 250t square. So they ask you to graph that with graphing calculators, which we don't use in this class. That's why I'm going to skip it. Okay, and how close the planes comes to each other, and at what time are the plane closest. So for this part, again, you need to use the graphing calculator, and technically from graphing calculator to answer that question, you have to use the minimum function on TI-84, which we're not using, so I'm skipping. You can read slide, if you have a calculator, it's not so bad, read slide 15. But again, this is something what I'm not going to ask on a test because we're not using TI-84 for this class, graphing calculator. So that's it from section 3.6. So you have all the sections, all the recording, and next video we'll talk about the review for a test. Okay, thank you for watching.